All right, so let's begin our class. So I don't have a slide this week. I'm going to write on my pad. So today we are going to talk about Stokes theorem. So let's begin with the Green theorem. Make sure it's recording. Okay, so what is the Green theorem? So it's about a line integral of a vector field along a curve inside two-dimensional space. So this is a curve which is the boundary of a region, D, two-dimensional region, and the orientation of the curve is always the direction when you move along that direction, the domain is on your left side. So that's a positive orientation, so-called positive orientation. So if you take the line integration of the boundary in the positive orientation, then the Green theorem says that it's same as the double integration of this value. And we say that this is the rotation, so it's a curl of two-dimensional vector field. Okay, so what's the Stokes theorem? It's similar, but we are looking at the two-dimensional surface inside of three-dimensional space. So this is our surface S. So it's similar to the Green theorem in the sense that the domain of integration is two-dimensional, D and S. It only differs by where this two-dimensional region is lying in. So in the Stokes theorem, we are talking about two-dimensional thing lying inside of three-dimensional space. So the boundary is C. 잠깐만요. 이게 좀 내가 까먹을까봐 잠깐 얘기할 거 있어요. Who needs a group? Okay, so I need to assign a group first here because I don't want to forget about this. 이유석. 같은 조예요. 네. 네, 같은 조니까 잘 기억하세요. Okay, so what's the Stokes theorem? So let's say we have a vector field inside of three-dimensional space. So that's my vector field F, whose components are P, Q, R. And it says if you take the line integration along the boundary of a surface, it's same as the surface integration of the curl of the surface. Now, it's obvious that I already gave you the direction of the boundary, that's your direction, orientation of the line integral. What's the orientation of a surface integral? Well, it also has to match with the orientation of the boundary. So the orientation of your surface is that if you walk along the boundary in the orientation of the boundary with your head up to the same direction of your orientation of the surface, then your surface must lie on the left-hand side of yourself. So it's same in the other way around. So if you have your orientation of surface, then your orientation of boundary is determined by in the same way. It's the direction where you walk along the boundary, then with your heads up to the orientation of surface, your surface lies on the left-hand side of you. So this is the Stokes theorem. So the surface line integral turns into a surface integral. So you can see that these two are not very different in the sense that it's about the equality between line and surface integral, and actually it's the same thing because you can see the Green theorem is a special case of the Stokes theorem. So if f is actually a two-dimensional vector space, vector field, but let's consider that the z component is 0, so it's actually three-dimensional vector field, but all the vectors are parallel to x and y plane, and S lies inside of xy plane, and the orientation is upward. Then let's plug that information to the Stokes theorem and see what happens. So our curl becomes this. So E1, E2, E3, del x, del y, del z, PQ0. So this is minus QZ. And then this is PZ and QX minus PY. And the line integration, so C is now the boundary inside of xy plane, it's just the curve in xy plane, and F dot ds. And before we put the right hand side here, let's modify our line integral a little bit here. So the boundary curve, let's see, is parameterized by the function x component function and y component function only, because we assume that S lies in xy plane, which means that z component is always 0, so we don't have to parameterize at all. So C prime t is x prime, y prime 0, and let's say t lies in the interval I, so then it's same as p x prime plus q. So let me write it one more step before I put this way. So PQ0 inner product. So I'm just following the definition here. Inner product with C prime, x prime, y prime 0 dt, and that is equals to I p prime q y prime dt. So it's same as p x prime dt, q y prime dt. So this thing is dx and this thing is dy. So therefore, it's same as integrating over the curve C of p dx, q dy. So that's same as integrating over two-dimensional vector field along the curve inside of xy plane. Now let's compute the right-hand side, the surface integral of the Stokes theorem here. So we already compute the curl, so I'm gonna put that in the equation. So it's minus qz pz qx minus py, and we assume that our orientation is upward, 0, 0, 1, and ds, and this is s. So you can imagine the s is actually d, because it lies inside the xy plane, but anyway, it's qx minus py, and then the s, so therefore, it's the same thing, so just the same thing as the right-hand side of the Green theorem. So these two things are the same due to the Green theorem. So the conclusion is that Stokes theorem is a generalization of the Green theorem. Okay, let's prove this. Maybe let's watch the example first, and then let's prove the Stokes theorem. So let's see here. Let F be a vector field defined this way. So this is how it's defined. So we have x, y, z as a coordinate of the point, and then it assigns to a vector defined this way. So the 1 over this square sum to the power of 3 over 2 is multiplied to every component here. And let's see, I have a surface given by the sphere on the upper half part. So it's that positive part. So it's the half sphere sitting on top of xy plane. So that's my S. And I assume that the orientation is, no, so not this orientation. Well, let's see. The orientation is N, and orientation of the boundary is this direction. So from now on, I'm going to write the boundary of a surface in this notation, the curly D and the S here. So that's the positive orientation of the boundary according to the orientation of the surface. So now I'm going to, let's say I want to compute the line integration. So by definition, if you want to compute the line integration, you have to parameterize the curve first. So here it's a simple curve. It only runs through the plane, xy plane, so it's simple. But if you want to plug in there, well, you can do it. But let's try the Stokes theorem. So when you try to apply the Stokes theorem, you have to check whether your vector field is well defined on the surface and the boundary. So this function, each component function of the vector field is well defined as long as x, y, z are not origin. So if x, y, z are all 0, then you have a 0 denominator. It doesn't make sense. But other than that, it's well defined. So you can use the Stokes theorems because surface S does not pass through the origin. So F is well defined on S and its boundary. So I can say it's same as the surface integral of the curl. And let's try to compute the curl. So the definition of curl, let me write it this way. If I have F to be PQR, it's RY minus QZ and PZ minus RX and QX minus PY. So here, PQR is given in the following formula. Let me compute this part first. So I'm going to take the partial differential of R, which is z over x squared plus y squared and z squared, 3 over 2, and subtract partial differential of Q in terms of z, x squared, y squared, z squared, 3 over 2. And, well, let's see. So z is constant when you compare, when you take the partial differential on y. So this is same as z times 3 over 2 x squared plus y squared z squared 5 over 2 multiplied to 2y, right? So and then on the right hand side, actually on the right hand side you only interchange y and z to get the same thing, so you can just switch the notation of z and y for the first computation. So it's y minus 3 over 2, 2z, and x squared, z squared, y squared, 5 over 2. And you can see they are the exactly same thing, subtracted each other. So you can see that it's 0. And you can do the computation for the y component and z component together, also in the same manner here, because we can just interchange the role of x and y and z to get the same conclusion. They are all 0. They are all 0. So what does it mean? The vector field that in the surface integral is 0 vector field, so nothing to compute. Nothing comes out, so it's 0. So the line integral integration is 0. Okay, so let's try to prove the Stokes theorem. So it's similar to the Green theorem, proof of the Green theorem, but here I'm going to split the surface into smaller pieces so that every piece can be represented as a graph of Z. So let's say S be the graph of function of Z, where xy lies in D, inside of xy plane. So S is somehow looks like this, and then I'm going to orient. So the orientation really doesn't matter. If I choose one orientation, then I choose the boundary orientation respectively. So if it happens to be the opposite orientation, everything changes its sign, but not changes its equality. So I can set any orientation here. So here is my S and D, and my parameterization is from xy point to xyz point, S, and sends xy point here to xyz point here. But z coordinate is depend on the evaluation of z using the function z function here. So this is parameterization of my surface S. So let's try the line integration part first. So I'm going to integrate the vector field F given by PQR. So P dx, Q dy, and R dz. So instead of using the notation inner product ds, I'm going to use this one because it's more convenient. Because here, I only want to get rid of this dz here. So how? So if you think about the meaning of dz, although I keep saying that dz has no meaning when you think about this in terms of the line integral, but now let's try slowly to give a meaning to this, because once you think about it's okay to think about dz with the meaning of the small increment of z. And how do you make a small increment of z? It's by small increment of x and y. So it depends on how much you change your coordinate xy into delta x and delta y amount. And for each amount of change, your delta z is going to change this much. So this is called a total integration. If you took the engineering mathematics, you have probably seen this before. But it also comes from the chain rule. So if you take the dt divided into the both sides, what you get is dz dt equals to zx dx dt plus zy dy dt. So in the left-hand side, it's z prime. So meaning that it's a derivative of z in terms of t, in a sense that we are talking about ddt of the function in terms of t, because x and y are now replaced by the function of t. So it's now a single variable function. So on the left-hand side, it's just simply zx times x prime t plus zy y prime t. And you can see that this is exactly same as the chain rule. So I'm going to replace that dz into this one. So what happens is it's same as the line integration of p dx q dy plus r zx plus r delta x. So here r zx dx rzy dy. So let's combine dx term and dy term. So this is equals to delta s p r zx dx and q r zy dy. And that looks similar to something we already seen. That's the left-hand side of the Green theorem, because it's all about x and y. And now, since we already mentioned it's about the dx and dy, we're not looking at the changes in the z direction. We only look at the changes in x and y direction. And x and y direction change governs exactly how the changes in the curve S, the boundary of S. So we can take the domain of integration to the boundary of D instead of boundary of S. So now it becomes up to here, it's integration on the boundary of D. And now it really looked like the left-hand side of the Green theorem. So this part is P, the capital P, and this side is the capital Q. So this is equals to, by the Green theorem, qx minus py dx dy. But then you have to be careful what the qx is. So qx is basically partial differential of q plus r zy. But here, even though everything large P, large Q is in terms of x and y, small p, small q, and also z, not z, sorry, z is x, y function, r function of x, y, and z. This small pqr is given as three variable functions, so you have to be careful when you take the partial differential there. So what we are taking the partial differential is q of x, y, and zxy plus rxy zxy times zy. So how do you take the partial differential of these type of function? So it's not just qx. You have to think about the partial differential of z times zx. It's a chain rule. It's a chain rule again. So you can imagine this is happening here. So you're taking a partial differential of qxy zxy. So this is a composition of q and s, the parameterization of surface. And this is same as qx times del x plus qy times del y del x plus qz del z del x. So y is independent to x, so it disappears, and x partial differential with x is simply 1, but z is not independent to x. The height of the function of the point on the graph depends on the change of x. So this zx doesn't disappear. So it's qx plus qz zx. And then let's take the next partial differential there. It's rx plus rz zx times zy plus rzyx. So that's your qx. And what's your py? It's del y of p plus rzx. So same thing applies here. Py, pz, zy plus ry plus rz, zy times zx plus rzy. That's your py. So when you plug these expression qx and py, this whole thing becomes integration over d of qx minus py plus qy disappears, qz zx minus pz zy and plus rx zy minus ry zx. And then you can see there is a canceling out. So this thing cancel out each other, and this thing also cancels out, right? They're the same thing, added and subtracted it again. So this is the final integration that comes from the line integral. So we just expanded the line integral part of the Stokes theorem. So now let's look at the other side, the surface integral part. And we're going to see that these two are the same thing. So surface integration part is the integration of these. And here, I need to take the orientation. So let's see, the f, and let's say orientation is n. So n is the orientation. How do you set up the orientation? So we decided that this is this orientation. So when you look up from the positive z-axis, it will wind the boundary of D in the counterclockwise direction. Therefore, the orientation n should move upward, is pointing upward. So therefore, this n has to be Sx cross Sy divided by the size of the cross product, because you want to go up. So the order of cross product must be this way. So what is Sx? By the way, so S is xy, zxy. So Sx is 1, 0, zx. Sy is 0, 1, zy. So therefore, Sx, Sy is minus Zx, minus Zy, and 1. So we're going to plug that in here over the S. So over the S. So now let's not put the S yet. We'll see that it disappears. So curl is Ry Qz Pz minus Rx Qx minus Py, and then orientation n. Well, now let's not put the n here, because eventually when you take the surface integral, then you only need to inner product the vector field with Sx cross Sy. So I'm going to put Zx, Zy, 1 here, and dx dy. So meaning that I'm not going to take the surface integral. I'm going to project my surface onto the two-dimensional domain D, so that I'm going to take the double integration over the D, because that's the domain of our parametrization. So let's expand this. So here we have Ry Qz minus Zx plus Pz minus Rx minus Zy, and Qx minus Py dx dy. There is some canceling out. No, there's no canceling out, right? So let's put this way. Qx here first, and then plus Qz and Py minus Pz and then we have R P first, Rx Zy minus Ry Zx dx dy. So look at this formula and compare the formula that we derived from the line integral. They are exactly the same thing. These two integrations are exactly the same thing. So we derive the same formula from the surface integral and the line integral. So they are the same. So that's the Stokes theorem. So what's the meaning of the Stokes theorem? So Stokes theorem gives you the meaning of the curl. That's the meaning of the Stokes theorem. So also there is a meaning to the application of electromagnetic theory. But anyway, so Stokes theorems gives meaning to the curl. So think about a very small circle loop around the point in the three-dimensional space. So we have a point x, y, z, and let's say we have a small radius epsilon, and a loop c epsilon is circulating around once around this point. So assume that there is a vector field. So here outside, and it actually in the space, three-dimensional space, there is a vector field, meaning that you can imagine that there is an airflow with the wind flow, and the vector field it's representing a wind direction and speed. Or you can imagine that there is a magnetic field or electric field inside of the three-dimensional space around the point. And if you take the surface line integration of this vector field, this is the work done by the vector field F around the point P. Okay? And Stokes' theorem says, okay, so let's assume that the vector field is well defined on the plane. So since I'm assuming this C epsilon is very small, so I can imagine the area, the planar area, the flat area surrounded by this circular curve is also flat. So this is my S epsilon. It is equal to the surface integration of S epsilon. So here, since I'm rotating in this direction, my normal direction, the orientation of my small surface S epsilon is pointing that direction. So the surface area of a surface integral is this one, and it's equal to the line integration. Since it's small, since I'm saying it's small, I can imagine that this is almost constant. Because epsilon is very small, so this double inequality means that it's way smaller than 1, so it's almost 0. So I can take out these, but before I do that, let's say I have to multiply the normal direction, and also this normal direction is also almost constant because I'm looking at the very small area inside of three-dimensional space. So changes in x, y, z coordinate, it's not much. So the normal direction is also not changing. And then ds. So you can see that the inner product between these two constant vectors are just constant number. So I can take out them outside of the integration. And this. And it says it's the multiple of the inner product of two constant vectors times the area of S epsilon. So what does it say? So the curl of vector field together with the normal vector n, it's same as the work done by the vector field around that point divided by the area epsilon. So it's same thing. So when epsilon is going to decrease up to 0, then it's going to be actually equal. So without epsilon going to 0, it's approximation, but when epsilon is smaller and smaller, then it's actually more accurate and accurate to approximate that vectors. That's a constant vector, so it actually becomes equal. So what's the left-hand side? So this means that it's the projection of the curl onto the direction of n. Because n is the unit vector, you don't need division of the size of n here. So it's a projection of the curl. So the Green theorem, so Stokes theorem says that if you take the amount of work done to circulate around one point, and then if you divide the area surrounded by the curve, that is approximately how much the curl is pointing at in the direction of that planar area. So for example, imagine this situation. You have a room, or you take the imaginary box inside of this the space, and there is a wind flowing in the space, and you have some propeller, which has no friction at all, so it can move without any friction. But it has to have a force, external force, to make your propeller rotate. So the reason why you put the propeller in the certain direction of wind blowing in certain direction and propeller is moving is because the wind is doing some work to rotate your propeller, right? So like a wind turbine, like something like that. So it means that if you want to know how much wind is rotating the propeller, is determined by where your propeller is pointing to. So if you have a three perpendicular direction that you can put your propeller facing to. So let's say you faced your propeller to the direction of positive x-axis, and you have a certain rotational speed of your propeller, and that speed is somehow measuring of the work done by the wind that rotates the propeller, and that is how much the work is and how much the vector field is rotating, and it's defined by the curl, and that represents the amount of the component in x direction of the curl, the vector field curl. So that's the meaning of a curl. And of course, there's more meaning when you talk about the magnetic field and the electric field, but we'll discuss that in the next time. In the more intuitive sense, with the wind or some velocity vectors, that's how you can interpret your curl. So before we move on to the divergence, I want to see if there is any questions so I can answer it. So usually they in the calculus they take Stokes theorem, something like technique that makes a complicated line integral into an easy computation of a surface integral and vice versa. But the real application of Stokes theorem is when you see the electromagnetic theory. So let's talk about it after we talk about the divergence theorem. So since there is no question, I can ask next time. So divergence theorem, let me state the divergence theorem. So we're going to talk about the volume, three-dimensional region, the volume V, and then its boundary. Now, the volume is finite volume, so it's surrounded by a surface without the boundary. So the boundary of a volume has no boundary. Okay, so this surface has boundary, no boundary. Now, we also assume that there is a vector field is flowing inside of this three-dimensional space, and what we are trying to compute is the divergence of this vector field inside the volume. And the divergence theorem says that it is same as the surface integration of the vector field throughout this boundary of boundary of this volume. and I put the circle around this double integration. It means that the surface that I'm going to take the integration on is closed surface, which means that it has no boundary. So delta V is a closed surface, meaning that no boundary. Okay. So don't confuse with the boundary of a three-dimensional area, a three-dimensional region, and the boundary of the surface. They are different notions. Okay. V has boundary as a surface, but this surface as a boundary of the region has no boundary because you don't have an end of the surface, right? Okay, so that's your divergence theorem. Let's prove this. And then let's see the example. So I'm going to assume that my volume is determined by two parts where x, y, z, where x, y lies in D and z is minimum, has minimum and maximum defined by the graph of G1 and G2. So in some sense, it looks like this. So upper part is the graph of G2 and the lower part is graph of G1. And when you project it down onto the XY plane, it has the same region D as a shade image of this. And so this is my volume V, and this is my XYZ coordinate. So let's think about the surface integration. So as I said, I didn't mention this one. So here on the left-hand side of divergence theorem, it's just the triple integration. Okay, so it's just the Riemann sum. On the right-hand side, you have surface integration. So therefore, we need orientation of surface. Here, orientation is always assumed to be outward orientation. So n is outward, pointing outside of the volume. Okay, so having that, the outside volume is this direction and this direction. So the direction is actually opposite when you look up upside and downside, but they are the same orientation because if you continuously move the outward direction from the upper side of the volume to the lower side of the volume, that matches to the downward direction of the orientation of the lower part of the volume here. So anyway, so I'm going to label it differently because I'm going to separate out these two surfaces. So this is S1 and this is S2. Let's think about the integration of S2. So by the way, so I'm computing the right-hand side of the divergence theorem. So this is split it into S1 integration and S2 integration. So let's talk about S1 first. So on the S1, what do I'm integrating? So I'm integrating PQR, the vector field, with the orientation N1 ds. And let's see, PQR is just PQR, but here everything is in three variable function, but z coordinates is defined to be the z defined by the value of G2. So that you should keep in mind. And what is n? So here N1, the orientation of S1 is pointing upward. So therefore, if S1 is the parameterization of the surface S1, and that is given by xy and G1 xy, then N1 is S1 cross S1x cross S1y divided by the size of that cross product, because I want it pointing upward. So this is equals to S1x cross S1y. And I don't need to plug in S1 because eventually I'm going to transform into a double integration on xy plane over the D. So that's what I have. And let's do it a little bit more. So it says it's the integration over D of PQR inner product. So remember how we got the cross product in that case. It's minus G1x minus G1y and 1 dx dy. So therefore it's integration over D of minus P times G1x minus Q times G1y plus R dx dy. Okay, that's the surface integration of upper part. So how about the surface integration on the lower part? So we have S2, the same vector field PQR, but now I need to multiply N2, the orientation toward the downward direction. So I need S2y cross product S2x instead, dx dy. So this is the integration over S2 of f. And when I do this, now I don't have to integrate over S2. It's about integration on D. And this is equals to PQR of, now think about when you change the order of the cross product, it becomes G2, wait, I interchanged the order here, so it's about, so let me fix this. So it's S2, S1, so S2, 1, it's G2, G1. G1, G2 is okay. Well, now what I just compute is, okay, I have to change the index here too. N1, N2, and then let's see. I'm integrating actually I'm integrating over S2, right? I think it's better to change the other way around. So let's say S1 first. So now I have to reverse the order here. So y and x, because N1 is now pointing downward. So it's a plus plus minus, and plus plus minus here. And when you do the S2 part, then you have to take xy. So minus G2x minus G2y, 1 dx dy. So it becomes d p G2x minus q G2y plus r dx dy. Okay, so let's combine these two. I'm going to add the integration over S1 and S2 together. So overall, if I integrate over S of this vector field, and this is going to be the same integration. So PG1x minus PG2x plus QG, is it 1? Yeah, 1 y minus QG2y plus, okay, so now it's weird. We have minus r and we have a plus r here. Are they cancel out each other? So they're not canceling out each other because, again, PQR is a 3-variable function, but we consider it as a 2-variable function by replacing the z coordinate. So here, when you take a S2 surface, z coordinate follows the graph of G1 function. On the S2 part, it follows the G2 function. So they're not the same thing. So here, the S2 part, R is considered as the value xy, G2 xy, and minus, on the upper part, when you have a minus R here, follows G1 function. So xy and G1 xy dx dy. Okay, so and same thing applies to the case for P. So let me rewrite here. Pxy here, this P is not, Z is replaced by the value of G1 xy and G1 x. And then here Pxy, what is it? Z, not Z, sorry, so G2xy and G2x, and same thing for Q, xy, G1 xy, G1y minus Q, xy, G2 xy times G2y and R. xy, G2 xy minus R, xy, G2 xy dx dy. What is this? Okay, so yeah, so that's the surface integration part. And now let's think about the triple integration part of the divergence theorem. So when you take the triple integration over the volume V of Px, Qy, Rz, dx, dy, and dz, what you can do is think about the volume integration into two parts. It's like something like an iterated integral. So on dx dy part, you only want to integrate over the range of z from g1 xy to g2 xy, right? That's what you want. So let's see. It's about d and px. So here, px is also x, y. Here, we don't take z as the function of x and y. It's a three-variable function, qy, x, y, and z, and rz, and x, y, and z here. But g1, g2 is a function of x and y, z, dx, and dy. So R part, so look at the R part first. This part is simple because what you're doing here is you take the partial differential of R in terms of Z and then integrate the Z again. So eventually you get the retrieve the R back by taking the integration by Z. So when you do this, then it's simply the R with the Z from G1 to G2. And look at this part. How do you take the integration of this part? So in some sense, you have to multiply. You have to think about this as a some differential in terms of z. There's a hint. So eventually, what we want. So this part is already retrieved by this part. So what we want is when you take the integration of these px in qi, what you want is to get these whole thing. This whole thing comes from the integration of these parts. Okay, let's think about the way I can do this. So let's think about this way. So if I take del z of p, let's see, how should I do this? So, G1 set. Z direction. DZ. Should think about this one. Let's see. It actually gets easier if I have split this surface integral into two pieces, because I already done this already, so I have no way other. So okay. So what I should have done, instead of putting PQR in the first place, what I have to done is that I had to split my PQR into sum of P00, 0Q0, and 00R, and I should have shown that the divergence theorem works for 00R in this case, and for other cases I have to split my volume V into different direction, so meaning that I have to represent my V by projecting onto other other plane, and then show the same way. But I've already done this, so I think it's getting a bit hard using this direction. So let's do it this way. So all right. So what I'm going to do is, assuming these PQ parts are all 0, okay? Okay. So instead of having PQ survived, I'm going to assume that these are all 0 here. So therefore, I don't have these two things, and these will just vanish. So also same thing here. It's all 0. So all 0 here. So everything goes vanished. So what happens? So this whole thing disappears. By our assumption, PQ is assumed to be 0. So there's nothing here. There's only these ones. Okay. So then what happens is there's nothing here because PQ is 0. We only have RZ. So what we are taking as integration is simply RZ over DZ. So we get this thing. So what is this? This is equal to plug in Z component as G2 value. So it's XY, G2XY minus RXY, G1XY. Okay? So it's same as integrating this function over dx dy, which is exactly same as our previous conclusion from the surface integration part. So when you do the surface integration, then you get exactly the same component, same conclusion from the triple integration. So you might wonder, okay, that's only when you have assumed that PQ is 0. So the fact is you can split your surface integration of PQR into 3 pieces. First, integration over 0, 0R, and second, 0Q0, and third, P00 ds. So what we have shown here is this part, the first part of integration, is same as integrating of triple integration of RZ dx dy dz over the volume. So this is done by projecting your volume onto the plane, and then your volume could be surrounded by graph of 2 functions, G1 and G2. Now for the other 2 sum ends here, so here I'm going to assume by cutting out the volume if necessary, that the volume is represented as a function of, in this case, x, y, z, where x, z is lying inside of the domain in x, y, x, z plane, and y is governed by size of functions, 2 functions, G1 and G2. So in sense, you're projecting your volume V on XZ plane, so here, and this is your D and this is your volume here. So since you are projecting in here, so you're cutting your volume into 2 pieces. So the boundary of V is now determined by the graph of 2 functions, G1 XZ and then G2 XZ. So with this observation, you can conclude the same thing, that this is equal to the integration now of Qy dx dy dz over the volume, the same volume. And this one, you do the same thing, then you can conclude that this is equals to the integration over the V of Px dx dy and dz. So if you sum over the same, the integration over the same volume, only differ by the function, it's a scalar integration, so you can put it in together, Px Qy and Rz dx dy and dz, and you can see that this surface integral on the left hand side is equal to the volume integration of the divergence of the vector field. So that's how you prove the divergence theorem. And actually the proof is not really important. What I want to emphasize is that, let me summarize what we have discussed so far, because they're all in the same idea, and actually they're in the same theory of integration. So let's start from the fundamental theorem of calculus. It says if I integrate the derivative from a to b, it's the difference of the function, or you can say it's the antiderivative of difference of antiderivative. And I think I mentioned briefly before, but integration on potential function says or gradient says that if you have a potential function of a vector field, and potential function gives the vector field by gradient vector field, and you want to integrate along the curve C from point P to Q, then it's same as the difference of the value at the starting point and end point. So that's the gradient. Integration over the gradient vector field, or you can think of in terms of the potential function. So if your vector field have a potential function, then any line integration over any curve is done by just taking the difference between the value of potential function. And let's now think about Green's theorem. It says it's the line integration of the vector field turns into a surface integration of a curl of a vector field, dx dy. And Stokes' theorem says a similar thing, but the curl is not a value anymore. It's just really a vector field. And divergence theorem is when you take the surface integral, it's same as integration of the divergence. They are actually the same thing. All the 5 theorems can be described in one single formulation. So I'm going to introduce some notation that used in the some advanced math courses, but I think it will help to understand why they are actually the same thing. So let's start from the fundamental theorem of calculus. So I'm going to denote my interval I as the notation AB, and I'm going to determine my boundary of interval. What's the boundary of interval? They are the 2 points, right? Point A and point B. So when you describe the boundary here, it's the same thing in the integration. You're integrating from A to B, right? So I need I need to distinguish the starting point and end point. So I'm going to write my boundary as a formal sum of 2 sets. So B minus A doesn't mean that it's the set minus notation. It's the formal sum, meaning that you just take the 2 sets as just the thing that you can add or subtract, but just the making signs on front of these 2 sets, and then you want to give a certain interpretation how you interpret these signs. So whenever I have this notation of formal sum, it means that if I take the integration on this boundary of some function, it means that I'm taking a set with a positive sign with a positive integration, and then minus sign with a minus integration. So here, what I'm integrating of is the integration of function f on one single point. So in some sense, I'm integrating over 0-dimensional space. So what is it? It's just the function value, and fb minus fa. Okay, that's what I meant by integrating over the boundary of I. So fundamental theorem of calculus says this is equal, fb minus fa is equal to f prime dx of the integration over I. Okay? So it doesn't matter whether a is less than b. A could be bigger than a. It only changes the sign of the result, but it coincides with this notation. So important thing is you have to remember this formula. Okay? And let's think about the potential function here. Potential function. The second equality here is that now you have a curve that joins the point P to Q of, and the line integration is the integration of the potential function, but then I can rewrite this in terms of dx dy notation. So it's the integration of the P, sorry, so qx dx and phi y dy. That's my integration. And what's the right hand side says? It's the boundary of C integrating the potential function. So here the same thing applies. So C is a curve joining P to Q. So there is a direction. So line integration always have a direction. So when you take the boundary of the curve C, then you have to distinguish which one is the start and which one is the end. So Q is the end, so I'm going to write this as set Q minus set P. Same way we describe the boundary of an interval. So this is same as the integral of phi at the Q minus integration of phi at the point P. So therefore it's phi Q minus phi P, which is same as the integration of potential function. So what you have to remember is this identity here. So potential integration of potential function can be described in this notation. Okay? And let's look at this part, these part. What is this? Phi x dx, phi y dy. Since phi is a two-variable function, I'm assuming the curve is inside of two-dimensional plane. So if I take this as a real valued function, what I'm doing here by phi x dx, phi y dy is measuring how much the value of function phi has been changed by the change of x and y coordinate. So if x and y coordinate changes by delta x, delta y respectively, then the value of phi changes this much. So this is exactly d phi. So I can replace this whole thing. So let me give a little bit of space in between here. So I can write this as integration of d phi over this curve. So remember this formula here. And with the same idea, let's modify our notation of fundamental theorem of calculus a little bit more. So look at this part, f prime dx. What does that mean? So f is a function of y, let's assume that. That means if I take f prime, then that's dy dx. So if I take f prime times dx, that means it's dy. So f prime dx measures how much the value of function has been changed by the change of x by delta x. So f prime dx is, in fact, df. It's same as integration of df over the line, over the interval I. So you have to memorize, keep in mind what this means here. So the fundamental theorem of calculus can be written as the integration of df, the small change of a function over the line, and it's equal to the total change onto the from the start point and end point of the function, and same thing for the line integration of potential function in two-dimensional space. So that makes sense. It really makes sense. But okay, so here I want to really emphasize. Don't think the fundamental theorem of calculus is something that you have a technique. It's the intuitive meaning. It's really a common sense. If you add up the difference of the value of function over the entire line, then what will be the result? It's the total change over the line, right? How do you measure the total change? You just take the difference between the start point and end point. Difference of the function value of function at the start and the end. That's what this fundamental theorem of calculus says. And here, it's the same thing. You have a curve, and you have a value assigned to each point. That's your phi. And you just add up all the small differences that you have along the curve. You just take the difference and add up all the differences. What you end up getting at the end is just the total difference from the start to the end. That's what the right-hand side says. So we want to generalize this idea to the higher dimension. So it's about the one-dimensional curve, one-dimensional interval, and one-dimensional curve. Let's generalize to higher dimension. That's the Green theorem. So Green theorem says okay, so on the right-hand side, I have the integration, double integration of qx minus py dx dy. And on the right-hand side, I have the line integration of p dx plus q dy. Okay, how should I interpret this? When you think about the line, the fundamental theorem of calculus and the line integration here, you can think about this as something that on the right is differentiated to make up the integrand on the left. So same thing applies here. You want to assume that this something on the right, that is the integrand over the line integral, is differentiated to make something on to the left of the integrand. So this is d omega here. So I'm going to introduce some notation that's called the form, but you don't need to remember the name here. So all the idea, it's the idea that you have to remember. So omega, this omega is called one form here because it has one d here. And when you take the differential of one form, you get two forms. So this is how you take the differential here. So first, you take entire p dx q dy into the differential operator. So d is somehow, it's the differential operator. On forms. And it's linear, so you can split your differential operator for each terms, d p dx plus d q dy. And on the first part, what you do is, it's just a definition again. It's a definition, p times dx plus dq dy. So in some sense, it's not really a rigorous meaning, but you can imagine that it's simply a measurement of how much it changed because of the changes in x and y or domain. So if you want to measure the change of p dx by the change of x and y, all that changes is from the p side. Dx is already a small increment of x. You don't change that change. It's going to be 0. So what you're going to get is a change of x component and some other component that makes up the change of the volume of area here. It comes from the change in P. So that's what we are doing here, dP, and also dQ part. And think about P. P is the two-variable function in this case. In the Green theorem, PQ are two-variable function. So dP, the total differential, or the change of the P part, is Px dx plus Py dy dx, and dQ is Qx dx, Qy dy. Now here you have some vanishing terms. Think about Px dx multiplied dx. What we want is how much the area is expanded, not the line, okay? Because we want to integrate over the area, d, on the left-hand side. Remember that d omega is for the integrand of the double integration. We want dx dy altogether, not just dx. But here, if you multiply px dx with dx, then you don't have dy term. It's going to be 0 anyway. So also same thing for the second part. dy doesn't give you any volume or area. So only this one survives. So we have py dy dx plus qx dx dy. Now, as I said, so now we are slowly give a meaning to dx and dy, although I mentioned that dx dy doesn't have a meaning. But now think about the meaning of dx and dy. If you take the order of dx dy in a reversed way, it means that you change the orientation. So if you look at dx first and dy next, it's something like you have x coordinate plane this way. But if you look at the other way around, yx first, then you have this, you are looking at the coordinate plane this way. So what's the difference? So if you rotate your second picture counterclockwise 90 degrees, then you have x here and y here. So these two images are actually a mirror relation. So if you winding counterclockwise direction in one picture, then you're winding the clockwise direction in the other picture. So they are in the mirror image. So in some sense, they have an opposite orientation. So when you take the surface integration, you want to take care of the orientation carefully, because orientation changes the sign of your result. So dy dx integration is actually the opposite orientation integration to dx dy integration. So you want to put the negative if you change the order of dx and dy. So it's py dx dy plus qx dx dy. So therefore, it's same as qx minus py dx and dy. That's your d omega, the differential of the omega, which is one form. And that is exactly same you see on the Green theorem. So what can you say about Green theorem? It's about the integration of d omega on the region, two-dimensional region, is same as the integration of the omega on the boundary of the region. So this is how you can write your Green theorem in a simpler way. Okay, well, let's generalize it to the Stokes theorem. So here we have Stokes theorem given as the following way. So we have a surface integration of the curl, which is ry minus qz dy dz plus pz minus rx dz dx qx minus py dx dy. That's the surface integration of the curl. And the Stokes theorem says it's same as the line integration of the boundary of the PQR, p dx, q dy, r dz. We're going to do the same thing as we done in the Green theorem, but now the only difference is that we have one more variable than before. The z components appears here, but everything is same. We have one form on the right hand side, one form, okay? And let's see what happens when you take the differential of this one form, d omega. So as I said, it splits into the sum ends of each component, dy, dr, dz, and same thing as dp, dx, dq, dy, dr, dz. And let's expand this here. It's px dx, qy dy, rz dz, and dx, and qx dx, qy dy, rz dz, dy, and rx dx, ry dy, rz dz, dz. Okay, same thing. There are many things vanishing. First, x cancel out, y cancel out, not canceling out, it actually becomes 0, and dz becomes 0. And let's see, there is dy dx term here and dx dy term here. As I said, if you change the order, you change the sign. So I want everything in the same order. We have dx dy. So qy, if you want the qy here, then you have in the dx dy order, you should put the minus, so qy. And how about the q, no, not the q, it's not, what? It's p, sorry, so why is it q? So here, it's not q, it's p. So it's py, pz, so it's py here. And then on the second term, you have a qx dx dy, so it's a qx dx dy, and so on. So let's put it all together. So dx dy term has qx minus py dx dy. How about dy dz? Dy dz come from here and here, right? So we have ry minus, here, why is it r? It's q here. So it's a qz dz, okay, so the sign is opposite, so r, qz minus ry. And then what's next? X, oh, sorry, so I want the yz, sorry. So I want y dy dz. So yeah, actually the first one is right. Yz means ry minus qz. And then the last one is what? Zx. So need pz minus rx dz dx. What do you see here? So you see exactly the same integrand appears in the Stokes theorems. That's the Stokes theorem, written in terms of the dx dy. So Stokes theorem can also be written as the following. Integration on the surface of d omega is same as integration of over the boundary of omega. That's your surface Stokes theorem. So Green theorem, Stokes theorems are the same thing. It's about the integration over the two-dimensional region. Okay? So same idea that you think about the fundamental theorem of calculus. It's about how to interpret the integration over the line component, the one-dimensional region. The Green and Stokes theorems generalize to two-dimensional region. Now let's look at the divergence theorem. So divergence theorem says integration over the volume of px qy rz dy dz is same as integration over the boundary of that volume of py dz qy pq z x r dx dy. So we do the same thing here. So take this as the omega. Now the omega has two d's in their summation. It's called 2 form. Let's take the differential of this 2 form to get 3 form. Same thing, dp dy dz plus dq dz dx plus dr dx dy. So what is dp? It's px dx py dy pz dz times dy dz. So let's forget the rest of the part. So here we have two dy's here. When you multiply these two, then it goes 0, and you have 2z dz here, so it becomes 0. So what survives is the px part. So we have px dx dy dz. And how about dq? From dq, only dy term survives, and the r part, rz part survives. But then I want to reorder dx dy dz so that it always has a dx dy dz order. So let's put the here dx to the front. So when I change the order of dz and dx, I have one minus come out, and another minus come out when I change the order of dx and dy. So then I have dx dy dz order, but I have two minuses, so it becomes a plus. And same thing for when I change the order of dz and the rz part. So I need to move twice, so I get change of minus twice. So everything is not changing. So it's a px plus qy plus rz dx dy dz. So that's your left-hand side integrand. So all the integration theorem are the same thing. It only differ by how much, what is the dimension of the domain of integration. Okay, there's something that I need to say about the orientation of this domain, but let's put it aside here. Okay, well let me give you one more example of a divergence theorem here, and then call it here. So let's put a vector field, the same vector field I gave you an example for the line integration. So here we have this vector field. I want to find out the integral of this vector field over the surface given by the surface of z equals to 4 minus x squared minus y squared, where z is positive. And the orientation n is upward. Okay, so I want to find out the integration of that vector field. So how do we find that? Okay, well, we have to decide what kind of theorem that we want to apply. Well, if you want to do it by definition, then you have to start parameterizing the surface here. That's not hard, but I think it's better to use the theorem, one of the theorem that we mentioned. So think about the Stokes theorems. So the surface integration in Stokes theorem is about the surface integration of curl. Here, I don't see directly the vector field is the curl of another vector field. So it's easier to use the divergence theorem instead. But however, when you try to use the divergence theorem, the surface has to be the closed surface. Here I'm talking about the open surface with a boundary here. It's not closed. So I need to find some way to close this surface out. Okay? So easy way to close this region bounded by the surface S is by putting this surface. Let's say this surface S is the upper surface, but what I'm talking about is the lower bound in the S prime. But in this case, if I use this S prime as another surface boundary of the region bounded by S and S prime, then the problem is I cannot use the divergence theorem because the vector field F is not defined at the origin. When x, y, z are all 0, then the vector field is not differentiable, not even continuous, not even defined. So I cannot use this flat surface to be a closed part of the closed surface. So instead, I'm going to use this surface, the surface that doesn't intersect the origin. So let's put the small sphere around the point of origin, and then put S prime to be the surface like this. So it's a subset. It's a union of annulus and then a small hemisphere with a small radius. So I took the small radius so that it doesn't intersect the boundary of the surface S. So what's the so I'm going to let the orientation of S prime also to be upward. So then if I want to use the divergence theorem, then I need to take the outward orientation from the volume bounded by S and S prime. So volume inside is here. Outward direction is n. So here n. When I look at the orientation of S, but the outward direction from the volume V on the S prime surface is actually the opposite direction of n prime. Okay, so if I want to keep the orientation of S prime to be that direction, then the surface integration of the boundary is going to be the surface integration on S with the normal direction n, and the subtraction of surface integration over the S prime with the n prime orientation right there. Okay, so that's what I'm saying here. Okay, so that's my surface integration over the boundary of the volume. Now, what does the divergence theorem says? So first, can I apply the divergence theorem here? Yes, because I don't have a point 0, 0, 0 inside my volume V. So the vector field is well defined. So I can use the divergence theorem, and it says the surface integration is same as the triple integration on V of the divergence of the vector field. And what is the divergence? Let's compute. So let's first compute the x component, the partial differential of the x component. So it's same as x squared, y squared, z squared, 3, and x squared plus y squared, z squared, 3 over 2 minus x, 3 over 2, x squared, y squared, z squared, 1 over 2, 2x. So it's same as x squared plus y squared, z squared, 5 over 2, and have x squared y plus z squared minus 3x squared. So that's the first part, the px part. So if you take the qx and qy and rz and add them together, you have 3 of these terms, and each term has minus 3x squared, 3y squared, 3z squared. So everything on the numerator cancels out to 0. So it's 0. The divergence is 0, so the volume integration is 0. So what does it say? If you want to compute the surface integration over the S, then it's same as surface integration over S prime. So you don't need to take the integration on the surface of S. Instead, you can just take the integration on S prime. Now, S prime consists of two parts. One is annulus, let's say S1, and the other is the sphere, hemisphere. So on annulus, I want to see how much it goes through perpendicular direction to S. So maybe I should make it into 3D picture here. So maybe some bigger picture. So on annulus part, this is my normal direction, which is 0, 0, 1. But on the annulus, what's the direction of vector field? Vector field has 0 z component, because this annulus lies on the 0, z equals to 0 plane. So all the vector field on the annulus is pointing perpendicular direction to the z direction. It's parallel to xy plane. So S2 integration, so if I take integration over S prime, it's same as S1 plus S2, but S2 part, there's nothing comes out because everything is running parallel. So same as integration over S1. Now, let's take radius of this hemisphere to be epsilon. So I want to parameterize my S1 into epsilon sine theta cosine phi, epsilon sine theta sine phi, and epsilon cosine theta. But eventually it will not really matter. So when I take the surface integration, it's 0 to pi, 0 to 2 pi, sorry, it's a hemisphere, so it's pi over 2. 0 to pi over 2, 0 to 2 pi. And well, what's the vector field? First, denominator becomes just the epsilon cube. And on the numerator, you have x, y, z. But what's the normal direction? So normal direction is same x, y, z. But now we have to divide by the size of this, so it's epsilon divided by. So and then you have integration, theta and d phi. But now you need a Jacobian. We already mentioned, I already applied the integration by substitution. The Jacobian is epsilon squared times sine theta here. So you have lots of canceling out. So on the numerator, we have inner product between x and y, z, x, y, z, the same thing, but so it's a size, x squared plus y squared plus z squared. That's the radius square. So radius is epsilon, so epsilon square. So and then on the denominator, we have epsilon fourth. And on the Jacobian side, we have epsilon square. And the sine theta here, and sine theta, sine phi. So epsilon all cancels out. It turns out that epsilon doesn't matter. So it doesn't matter how small you choose the hemisphere, as long as it doesn't penetrate, it doesn't intersect the origin, you can always get the same integration as a surface integral. And phi is 2 pi, and you take the sine integration to get 1, so it's 2 pi. So overall, the surface integration is 2 pi. You can check that it's the same thing by using the definition from the original surface S instead of S prime. So next time I'm going to talk about how you're going to apply this Stokes theorem and divergence theorem in the electromagnetic situation. And also I'm going to give you some pseudocode for doing the last project. So could you raise your hand if you're doing the 9th project for the second project? Anyone, the Maxwell equation project? Raise your hand if you're doing the Maxwell. So I haven't think about the good way of putting it into a game, but you don't have to follow the exact way I'm doing this, but what I'm thinking about as a project is trying to visualize and make it into game about the magnetic field of dipole. So you have a magnetic thing going on, like a dipole or some magnetic road, then you have a magnetic field around this dipole, right? So maybe I'm going to make it into a three-dimensional figure, and then using some projection so that you can manipulate the rotation of the projection, so that make that into some sort of a game. But I'm not sure whether it's going to be a nice application or not. But anyway, so it's going to be some application of the of understanding of electromagnetic field theory. So let's discuss that in the Friday and see what happens. All right, so as I mentioned that this week we're going to finish up the entire lecture, and next week we're gonna spend some time for you guys to prepare your presentation, and I'm going to walk around in the class to see whether I can give some feedback before real presentation, because we're not gonna have a pre-presentation this time. So, and also we need to finish in a tight schedule. We have to do it in 2 lectures on the final week. So if your group member haven't come these days in the class, then make sure that your group member come to the class next week, at least next week, so that I get the sense of what you're doing for the second project. Because as I mentioned, the project is the only component so far that I can give you the grade. So if one of your member of your group doesn't participate in your project preparation, you can be harsh on them, because I don't want a free rider. Okay, so you can either make them work or let me know that someone is not participating, so that I can do something on him. All right, see you on next Friday. See you on Friday.